Welcome to this exciting journey into the heart of calculus. Today we are going to start mastering the limits of functions. Think of this as your visual passport to understanding how math deals with the concept of getting closer and the vast mystery of infinity. Don't let the symbols intimidate you. We are going to break down every approach and every curve together. By the end of this guide, you won't just see functions as lines on a page, but as dynamic paths leading to fascinating destinations. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's start by clearing up a common confusion: the difference between where you are and where you're going. On the left, the exact destination is like looking at a point on a map and saying, I am standing exactly at x0, y0. In math, this is simply the value of the function. F of x0 equals y0. But on the right, we have the approach. This is the magic of the limit. We aren't interested in what happens at the point, but rather where the function is trying to go as we get closer and closer. We call this the target. The notation is lim as x approaches a of f of x equals L. Remember, we are approaching without necessarily touching. It's the journey that counts here, not the arrival. Now, let's look at a classic troublemaker, the function f of x equals 1 over x. This is a perfect example of why we need to look at both sides. If we approach 0 from the left, denoted by 0 minus, the red dotted line, the function dives down toward negative infinity. But if we approach from the right, 0 plus, the green dotted line, it rockets up to positive infinity. Because the left limit and the right limit don't agree on a single target, we say the overall limit at 0 does not exist. It's like two friends trying to meet at a mall, but one goes to the roof and the other to the basement. They never actually meet. Sometimes a function hits what I like to call the wall. Look at this graph. As x gets closer to the value a, the curve shoots up toward positive infinity, plus infinity. It gets infinitely close to that dashed red line, but it never ever touches it. We call this vertical line x equals a vertical asymptote. In limit notation, we write that the limit of f of x as x approaches a is plus infinity. It's a way of saying the function grows without any bound whatsoever as it nears that specific x value. It's like a rocket that never stops accelerating. Let's look at the big picture. What happens when we look way out to the left or right of the graph? On the left side of this slide, we see a function escaping to infinity. As x grows larger and larger, x approaches positive infinity, the function just keeps climbing. It has no ceiling. But look at the horizon on the right. As x moves toward infinity, the curve begins to flatten out, settling toward a specific value L. This horizontal dashed line, y equals L, is called a horizontal asymptote. It's like the horizon line at sea. No matter how far you sail, you're always heading toward that steady level. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. How do we actually calculate these things? Think of it like a game with 3 levels of rules. Level 1 is the green light. If you're dealing with normal, finite numbers, just plug the number in. Direct substitution. The limit of a sum is the sum of the limits, and so on. Level 2 is playing with infinity. Here, common sense is your best friend. Adding a number to infinity is still infinity. L plus infinity equals infinity. Now, check out the pizza analogy for division.
If you have L pizzas and try to share them with an infinite number of people, everyone gets essentially 0 slices. L over infinity equals 0. But watch out for level 3, the danger zone. This is where infinities clash, and the rules aren't so simple anymore. We'll need special tactics for those.
Welcome to the indeterminate forms. These are the 4 mathematical battles where we can't tell the result just by looking. First, infinity minus infinity. It's a tug of war between 2 giants. Who is pulling harder? Second, infinity divided by infinity. A race between 2 rockets. Which one grows faster? Third, 0 times infinity. Absolute nothingness versus absolute everything. Who wins? And finally, 0 divided by 0, a microscopic battle at a single point. When you see these, don't panic. It just means the function is wearing a disguise. To solve them, we have to use algebra to unmask the real limit. Ready for a pro tip? Here is the ultimate hack for limits at infinity. When you're looking at a huge polynomial like 3x cubed minus 4x squared plus 7 as x goes to infinity, the smaller terms, like minus 4x squared and 7, become completely insignificant compared to the boss term with the highest power. In this example, as x goes to infinity, the function behaves exactly like 3x cubed divided by 2x cubed. We can cancel out the x cubed terms, leaving us with a limit of 3 halves. It's like comparing the weight of an elephant to a few ants on its back. Only the elephant really matters for the total weight. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Meet one of the coolest tools in calculus, the Squeeze Theorem, also known as the sandwich. Imagine a wild function f of x that is oscillating like crazy. If you can trap it between 2 well-behaved functions, g of x and h of x, that are both heading toward the same value L, then f of x has no choice but to be squeezed toward that same target. It's a brilliant way to tame functions like sine of x over x that look messy but actually have very predictable behavior as they head toward infinity. Let's summarize the geometry of asymptotes so you can recognize them instantly. 1. Vertical asymptote. The function explodes to positive or negative infinity as x nears a specific number. 2. Horizontal asymptote. The function settles down to a flat line L as x moves toward the far ends of the x-axis. 3. Oblique asymptote. This is when the function approaches a slanted line, y equals ax plus b. The trick here is that the vertical distance, the difference between the curve and the line, shrinks down to 0. It's like the function is trying to become a straight line in its old age. Time for a masterclass. Let's solve a 0 over 0 indeterminate form step by step. Step 1. We try direct substitution for x equals 2 and get 0 over 0. Oh no, a disguise! Step 2. Time for algebra. We use the recall box formula to factor the numerator. X cubed minus 8 is a difference of cubes, becoming x minus 2 times x squared plus 2x plus 4. Step 3. The magic moment. Notice we have x minus 2 on top and bottom? We cancel them out. That x minus 2 was the troublemaker causing the 0. Step 4. Now that the disguise is gone, plug in x equals 2 again. We get 4 plus 4 plus 4 equals 12. Mission accomplished. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Whenever you face a limit problem, follow this limit solver's algorithm like a map. Start by substituting the value. If you get a real number or an obvious infinity, you're done. Success! But if you get an indeterminate form, fi, you must identify the battlefield. Is x going to infinity? Use the highest degree hack. Is x going to a number resulting in 0 over 0? Factor it out or use a conjugate. Are there trig functions like sine or cosine? Reach for the squeeze theorem. Simplify, cancel the problem, resubstitute, and you've got your answer.
Look at how much ground we've covered. This mind map shows how all these concepts connect. We've got our standard limits, like sine of x over x equals 1, that act as our building blocks. We have our definitions of what a limit is, the 3 types of asymptotes that shape our graphs, the powerful theorems like the squeeze theorem, and the 4 indeterminate forms that we now know how to defeat. You have all the tools in your belt now to tackle any limit that comes your way.
Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. What a wonderful way to wrap up our journey into the world of limits. This quote is so powerful. Limits are not boundaries. They are the tools to understand the infinite. In everyday life, a limit often feels like a wall or a restriction. But in mathematics, a limit is actually a bridge. It is the tool that allows us to peek over the edge of the finite and see what is happening at infinity, or to look deep inside a single point to understand instantaneous change. Without limits, we would not have derivatives, integrals, or modern physics. By learning how to calculate them, you are not just solving homework problems. You are learning the language of the universe. Thank you for your incredible attention and hard work. Remember, whenever you feel stuck, just look back at your tools, trust the process, and keep exploring. The infinite is waiting for you. Great job.